In dense cities, land cannot expand outward, so housing climbs. Rooftop dwellings appear in Hong Kong, Cairo, Mumbai, Manila. This is not a visual novelty. It is vertical pressure redistribution. A reinforced concrete roof slab is engineered to carry two types of weight: dead load and live load. Dead load means the permanent weight of the structure itself, the slab, waterproofing, insulation, and any fixed equipment. For a typical urban roof, this comes to 2.4 kilonewtons per square meter. Live load is the variable weight from people, movable objects, or temporary installations, maintenance crews, snow, or, in the case of rooftop housing, daily residential activity. Most building codes set this live load at 1.5 kilonewtons per square meter for residential roofs. Add these together, and the standard roof slab is designed for a combined load of roughly 4 kilonewtons per square meter. This is a ceiling that defines the safe boundary for what the structure can bear. Consider a slab thickness of 150 millimeters, common across Hong Kong, Mumbai, Manila, and Cairo. This dimension, along with the placement of steel reinforcement, determines how the roof transfers weight down to the building's columns and foundation. The slab's strength is not limitless. It is calibrated for a specific load profile, with safety margins set by engineering codes. When a rooftop water tank is added, for example, the load is not spread evenly. A 2,000-liter tank, enough for a small household, concentrates nearly 19.6 kilonewtons onto a footprint of just 2 square meters. That is almost 5 times the live load the slab was designed to carry in that spot. Each informal dwelling, each additional tank, shifts the balance and introduces new stresses that were never part of the original design. Over time, as these loads accumulate, the slab's safety margin narrows, and the risk profile for the entire building changes, often silently and without immediate warning. Land scarcity sets the rules in Hong Kong's Central and Western District, where a square meter costs nearly $22,500, more than twice Manhattan's rate, and far beyond what is seen in Cairo or Mumbai. For most residents and small developers, these prices close the door on legal expansion. Rent-to-income ratios offer no relief. In both Hong Kong and Manhattan, over half of median household income goes to rent. In Sham Shui Po, one of Hong Kong's most crowded neighborhoods, the poorest families spend 35 to 50% of what they earn just to keep a roof overhead. Subdivided flats and rooftop structures fill the gap left by public housing, which is stretched thin. More than 180,000 households in Hong Kong wait over 5 years for a spot, while New York and Chicago face similar queues. Zoning laws tighten the squeeze. Floor area ratio limits, set at 12 in both Hong Kong's core and Manhattan, cap how much can be built per plot. Securing approval for legal rooftop conversions can take up to 2 years, and it demands costly compliance. When these limits are reached, the roof becomes the only available space, though it sits outside the official development envelope. Informal rooftop units built without permits offer a faster payback, 3 to 5 years, compared to a decade for legal additions. Economic logic, shaped by high land prices, rent burdens, and slow approvals, drives the rise of informal vertical expansion, even when buildings were never designed for it. Structural fatigue in reinforced concrete begins quietly, often invisible to the naked eye. Each time a rooftop slab bears the weight of a resident, a water tank, or a new partition wall, it experiences a load cycle. Laboratory studies in Mumbai have shown that when these cycles exceed 30,000, especially under sustained overloads, fine cracks begin to propagate through the concrete. These cracks, though small, create a pathway for water to reach the steel reinforcement inside the slab. In coastal cities like Hong Kong, chloride-laden air accelerates corrosion, with public works data recording rebar loss at a rate of 0.02 millimeters per year. Over a decade, this can reduce the cross-sectional area of the steel by nearly a fifth, quietly undermining the slab's strength. To quantify this risk, Structural engineers use the Safety Margin Index, or SMI. The SMI combines the ratio of a slab's design load to the total imposed load, including every informal addition, with factors for code compliance, utility capacity, and exposure to wind or earthquakes. When the SMI drops below 1.0, the building is operating beyond its engineered safety envelope. In practice, buildings in Hong Kong's Central District average an SMY of 0.86, while some in Manila's Tondo District fall to 0.88. Documented failures, from water tank collapses to typhoon-induced roof failures, have all occurred at SMY values below this threshold. The SMI provides a diagnostic lens for identifying when cumulative, incremental changes push a structure from resilience into hidden risk. Regulatory oversight for rooftop housing operates in a legal gray zone, shaped as much by resource limits as by statutory design. In Hong Kong, the Code Compliance Score, an aggregate measure of structural, zoning, and safety adherence, rarely exceeds 0.7 for high-rise districts and drops to 0.5 or below in informal sectors like Dharavi or Tondo. This score reflects both the frequency and rigor of inspections. Mandatory checks in Hong Kong occur once per decade for buildings above 3 stories, while Mumbai and Manila rely on annual or ad hoc audits that reach only a fraction of at-risk rooftops. In practice, most informal rooftop structures are never formally assessed unless prompted by complaint or visible hazard. Liability for structural failure in these settings is often diffuse. Unauthorized additions fall outside the protection of standard property insurance policies. In Mumbai, after a rooftop fire in 2012, the insurer denied all claims, citing explicit exclusion of unpermitted structures. Similar clauses appear in Hong Kong and Manila, where policies reference non-compliance with local building codes or occupancy permits. For owners, this means that any collapse or damage, whether from overload, water infiltration, or fire, becomes a personal risk, not one shared by the insurer or the municipality. The result is a system where structural risk is externalized. Municipal authorities lack the capacity to enforce code compliance at scale, while insurance exclusions and legal ambiguities transfer the burden of failure to individual residents and landlords. As more rooftop dwellings are added, the formal mechanisms designed to safeguard building integrity become less effective, and the cumulative risk migrates from material stress to legal and financial uncertainty. Water, power, and drainage in high-rise buildings are engineered for a fixed population. In cities like Hong Kong and Manila, water systems are set to 400 kilopascals, with rooftop tanks capped at 1,000 liters per 100 square meters. When unauthorized rooftop units appear, tank volumes swell and push pressure past safe limits. In Sham Shui Po, 2019, overloaded tanks forced emergency shutoffs, leaving lower floors with unreliable water. This is a strain on water. Electrical grids face similar strain. A 40-story building's 500 kilovolt ampere transformer is sized for legal demand, but each rooftop addition, such as air conditioners, lights, and appliances, can draw 30 kilowatts. Clusters of these units can push demand up by 150 kilowatts, nearing the transformer's threshold. Utility records in New York show transformer trips rising 12% in buildings with illegal rooftop conversions. This stresses electrical systems. Drainage systems, built for 2 liters per second per 10 meters, clog as new surfaces double runoff, overwhelming gutters, and flooding basements during heavy rain. This overloads drainage. An informal rooftop dwelling in Hong Kong or Manila can be built for as little as $10,000 to $15,000, a fraction of the capital required for a legal unit on the open market. Rents for these structures, even in dense districts like Sham Shui Po or Tondo, range from $300 to $500 per month. For a small-scale landlord or family, the math is straightforward. At $400 per month, the initial outlay is recovered in just 3 to 5 years. In a market where legal expansion is blocked by zoning caps, and the cost of land exceeds $20,000 per square meter. Informal rooftop construction offers a rapid return on investment that formal channels cannot match. But the costs that make these units affordable upfront are deferred elsewhere. The slab beneath each new room absorbs additional load, accelerating fatigue and corrosion. Insurance rarely covers unauthorized structures, so future repair or collapse becomes a personal liability. Utility upgrades are not factored into the initial budget, leaving water, power, and drainage systems to absorb the strain. The short payback window rewards immediate affordability, but leaves hidden liabilities, structural, legal, and financial, to accumulate over time. In this system, the benefits accrue quickly to those who build, while the risks compound quietly for those who remain. Wind and earthquakes impose limits that adaptation cannot erase. In Hong Kong, high-rises face a design wind speed of 55 meters per second. In Manila, it is 60 meters per second. Typhoons regularly reach these speeds. Rooftop additions built outside code rarely match the original wind resistance, and uplift on lightweight steel or water tanks can cause wind effects to jump from 40 to 60 meters per second. Local pressures then exceed the 2.5 to 3 kilonewtons per square meter that slabs were meant to resist. Failures are well documented. Rooftop rooms or tanks have been torn away, slabs exposed, and deterioration set in motion. Seismic forces amplify risk. Mumbai's seismic coefficient is 0.15 G. Extra mass at the roof lengthens the building's natural period, concentrating earthquake forces at the top. A 30% roof mass increase can push lateral loads past what columns and joints can handle. After recent earthquakes, buildings with unauthorized rooftop structures showed more slab cracks and column distress, even when shaking stayed within code. Hazard multipliers set the boundary for resilience. Rooftop housing is not an anomaly. It is a signal. When land scarcity outpaces policy reform, cities grow in layers, even when those layers were never engineered to last. The real question is not where the next room will go, but how much more strain our structures and our policies can bear.